The purpose of this lab was to analyze motion of a free-falling object using Tracker and to program a computer model to accurately predict changes in position of the object as it fell to the earth over time. In this experiment, I used the Tracker program to analyze the motion of a beach ball falling to the ground from a height of about 2.5 meters. The motion of the beach ball was recorded using a digital camera, and the video was uploaded into Tracker for analysis. The beach ball was dropped from rest and fell approximately straight down. The beach ball was filled with air and less dense than a rock, so it met the requirements specified for the lab as an object falling somewhat slowly. To get the best results from Tracker, I specified the video frame to exclude the beginning motion, and I specified small video frames for analysis, checked the video timescale for compatibility with my camera, chose a coordinate system orientation with the origin placed at the center of the beach ball, assumed to be the actual center of gravity of the approximately spherical ball, and with the motion of the ball moving down the y-axis in the negative direction. I identified the ball's position from frame to frame using the point mass option. The beach ball's initial position was 0, 0, negative 0.01. The beach ball's second position, needed to compute initial velocity as specified in Tracker, was 0.0330, negative 0.073. Initial velocity was calculated using the average of these two data points and the definition of average velocity, which is delta r over delta t. Initial velocity equaled negative 1.9. Also, the last observation used in the analysis was 0.4670, negative 1.754. Fnet was assumed to be unequal to 0 and velocity varied over time. I constructed a computational model based on Newton's second law, or the momentum principle, that included only the effect of gravity. For this model, Fnet was assumed to be equal to the weight of the ball, or mass times acceleration due to gravity. The model did a good job of predicting values at early times, but as time increased, the accuracy of the model decreased. The data suggested that the model was over-predicting position for a later time, suggested that air resistance was significant. Next, I constructed a computational model also based on Newton's second law, or the momentum principle, that included the effect of gravity and the effect of drag. I modeled the effect of drag as a turbulent drag force whose direction was always opposite to the direction of the object's motion and whose magnitude was proportional to the square of the object's speed. I estimated a proportionality constant for magnitude of drag force value using an iterative process of running the model with different estimated values of the constant until the last predicted value was close to the last observed value. I determined the proportionality constant to be equal to 0.0001. Using this value resulted in a model that was close to the observed values. Next, I compared my model to my observations by plotting position versus time, the predicted position versus time for my first model, and predicted position versus time for the second model in the same graph on an Excel spreadsheet. Both models gave reasonable predictions but were more accurate at earlier times. I observed that the model, which included drag, predicted a terminal velocity, or a velocity. Then I adjusted the model to consider the situation where the ball was thrown, not dropped from rest. The new model predicted a higher terminal velocity.